Hello everyone, my name is Robin Filtoriano. I am an AI and ML master student, and today I'm going to discuss about superfactor machine for classification problem. Before we dig deeper into this presentation, let me tell you the definition of superfactor machine or SVM. So SVM is just a supervised machine learning algorithm that could be used for either classification or regression problem. For example, we have two data classes and 5 lines. In this picture, we could say intuitively that the red line is the best line to separate these two classes because it is the most general line. Therefore, SVM used this concept. So the goal of SVM is just to find the best separating hyperplane. And because this is a line, we could express as a linear function that is W transpose X plus B, where W is our weight and B is the bias. Okay, the history of SVM is in 1962, Fabnik and his friends proposed the first general ideal of SVM, and then in 1999, they introduced a nonlinear classifier using a kernel trick, and now SVM is widely used for classification problem. For me, SVM is interesting because later in this presentation, I will show you how does a linear hyperplane could separate a nonlinear data. Okay, there is some terminology in SVM. So suppose we already found the best separating hyperplane, which is the red line, and you could see in this image, you have an upper and lower bound. And if the factor located in that bounds, we call that factor as a superfactor, and the distance between that bounds, we call that margin. So how could we find the best separating hyperplane? The answer of that question is simple. You just have to find hyperplane with the maximum margin. So now we have an optimization problem with our objective function is maximize the margin and with these constraints. Observe, this optimization problem is convex so that we could always find global maximum for this solution. After several steps, we could optimize this problem and we could obtain alpha value. So our final SVM equation would be as follows. Another interesting thing is about the kernel tricks. For example, we have -1, 0, and 1 as our data, and we only have two classes. As we can see in this picture, our two classes cannot be separated with just a linear function. Suppose I have a P function which transforms one-dimensional data into a three-dimensional data. And now in this picture, we could see we could separate those two classes using a linear hyperplane. Recall, in our SVM equation, we have to do a scalar product calculation. Therefore, we do this calculation and the result is 0. However, this calculation could be huge if our initial input data has already a big dimension. This problem usually called a curse of dimensionality. Therefore, I have a polynomial kernel function with this form where R, C, and D is just a hyperparameter that we have to choose. And when we plug in the same value, the result is same, 0. Therefore, a higher dimensional feature space calculation, which is the pi function calculation, can be calculated in the original input space dimension just using the kernel function. Okay, let me give you some code. In this example, I have 1000 data and my goal is to classify the red and the blue data. We know that there are no linear functions that could classify this type of data. However, using SVM and RBF as its kernel, we could see that the model could classify the data correctly. So the conclusion of this presentation is, first, SVM became the mainstream of machine learning and contributed to statistical learning around the year 2000. SVM has the form of simple linear model, and the optimization problem of SVM is convex. And also, it could classify nonlinear data using a kernel trick. However, there is one problem, is which kernel should we choose for our dataset? Okay, that's the end of my presentation. These are the references that I use. Thank you.